Hello, everyone. Thanks for joining. Uh, yeah, so let's get started. So first of all, I'm Siddharth, and I am a computational psycholinguistics or computational cognitive linguistics. It's always a discussion what to say, and it's about how you feel that day, I think. So yeah, so I am a researcher at Potsdam University. I started my PhD 1 year back, and it has more to do with how humans understand sentence processing, like when you hear a word, a sentence, what happens in your brain at an electrochemical level. So we try to understand that, and we try to also use language models to sort of complement our theories. And my hobbies include music, listening to, I'm not still there with playing it, hopefully someday, and chess a bit. I've been to chess tournaments as a attendee, and also when I was young, I used to play a lot. So, and football, of course. But then when your team is bad, you stop watching it for 4 years. So, yeah, I think it's an old slide. I should edit. It's football. It's an own goal now. And yeah, I mean, I like to do comedy when I'm free, when I get time, which is difficult, but yeah, keeps the winters more interesting. And then, of course, sleeping, because it's good if you are into sleep, if you like sleeping, because we do it half of our day. So I think that's a plus for me. I like it. So let's see what we are going to talk about today. So the topic of today is tokenization, uh, and we will talk about how text is represented in these models, computers, digitally. What are the challenges of tokenization? What is tokenization? What are the challenges I ran into? What are the challenges other people have run into? And yeah, a lot of interesting aspects from that side. Types of tokenization, a very brief overview, so that it's a full-fledged sort of coverage of the topic. And if you have never heard the word tokenization, at least you'll remember what it is, and what are the kinds of it, and why do we have these different kinds, and how we came to where we are right now. Gotchas, that's where it will get interesting. That's where I ran into issues. That's where other people have run into issues. And that's why you, as a user of these LLMs, you, as a designer of these LLMs, should keep in mind, so that these things don't happen and new things happen. New bugs are better than repeated bugs. What is Surprisal? So Surprisal is a key component that we look into, definition that we sort of derive from large language models, and I'll talk about what it is and what's its role, and what's the role of tokenization in Surprisal. Real life examples of where tokenizer failed. Yeah. So how do we represent input text, right? So as human beings, we learn to speak before we learn to write. And that's not the case with LLMs. You have to teach them with a model that can be sort of represented in digits, right? Because that's how computers work, 0 and 1 at the end of it. So for example, something like keyboard not found, which is a popular meme where you see this F10, press F10, keyboard not found. So this sentence will become something like 12, 23, 567, keyboard represented by 12, not by 23, found by 567. This is a very low-level example of it. So what is tokenization? So because these systems cannot understand keyboard not found, you have to come up with something, some mechanism to convert this into numbers, so that computers can understand it. So when you break a text, so first of all, you break a text in small units, tokens, subwords, and so on, and then you sort of map it to a sequence of numbers. So these small elements are called tokens, and their corresponding values are their encoding, or their representation in the numeric form. So tokens can be words, subwords, or characters. Each token is mapped to a unique ID, as you can see in the above example. Yeah, but things don't go as we want them to go. So let's see some examples. So as I said, it can be anything, right? Token can be a subword, and word, or signals. So expectation, if you don't know anything about token, you'll be like, probably it's just a word. But reality is that it's much more complicated depending on how you have designed it, which model are you using. So in reality, hello is not equal to hello exclamation, capital H, hello. and hello with a space on either side or in somewhere in the middle. It's not equal at all, because in language, in textual language, you will have information at every aspect of it, right? If you have an exclamation mark, you have an expression. If you have a capital H, maybe it's the beginning of a sentence. Maybe when it's the beginning of the sentence, you have no prior context. If it's at the end of a sentence, you will have a different representation. And you can see there are two hellos that look exactly the same, but maybe they are not, because Unicode, it changes everything. Your E from a different language would look the same, but it would be different. So when working with LLM encodings, remember, and this is a very good quote that I like, whatever you think matters, whatever you don't think doesn't matter may also matter. And it's it's a quote by me. So I think it's sometimes we take things for granted. We think LLM, like a GPT-based model, like a Chat GPT-based model, would encode things in a certain way, but you are always in for a surprise unless you read how they have processed their encodings. So from here, we go to types of encodings, a brief overview. So first of all, these word-based tokenization, where you just split the word depending on how it is implemented. You establish clear boundaries between the words. And then there is character-based tokenization, which is you take one character at a time and you break it. It's very good for morphologically rich languages. For example, Japanese. I tried learning, but just a warning, doesn't work out very well. Yeah, but I still watch anime with subtitles. So when you have a morphologically rich language like Hindi or Japanese, then character-based encoding is powerful because you have a lot of information encoded in a single character, which is not true for something like English, where word-based tokenization is good. But of course, there are issues with each of them. Character-based encodings, you can cover the entire Unicode, which is 1.150K, 1,000 Unicode characters. And then you would have nothing that is out of vocabulary, right? Because you just take every possibility in account. But if you take word-based tokenization, then the problem is that you would not have everything. You would have new words. You would have Danke. You would have Schadenfreude. You would have a lot of new words that are not part of your lexicon, and you'll have to sort of think on the ways to tackle them, because if you put all of them unknown, then of course that all of these words as a single unit would have a huge representation, which may not be good for your model training. So we come up with something of a solution in between, which is a subword tokenization, which is neither a character nor a word, but a combination of these sort of characters. So the characters combine to become subwords, but never really grow up, may not really grow up to become whole words. So this is kind of like a compromise of a situation where you are in between. So for example, uh, there is a tokenizer playground by OpenAI where you can just type a text and see how OpenAI is breaking that text. And then you can also select which model do you want to see is breaking the text. So all these different models will tokenize the same sentence in a different sense. So I think it's a good playground. For example, I was having one discussion with one of my German friends, and they said that how is ChatGPT is not making the language gender inclusive, because if you know a bit about German, it's very difficult to talk about the third gender or anything beyond the binary because the language is designed that way. So then I just told them to use this GPT, use this playground tool to see how it is breaking the word, and this was a good start into our discussion. So I would highly recommend you to go to this website and see how this tokenization is taking place. For example, this is for GPT-3, I guess. So you can see this food is the hello world programming is in itself a set, but then when I tastiest, of course, it's an ungrammatical sentence, but I wanted to have this one word which actually has subdivisions in itself. So this tastiest, as you can see, is not a word, but it's also broken down into 3 subwords, thanks to our byte pair encoding, which is this compromise sort of. Yeah, so very briefly, how byte pair encoding works. So you start with all the characters, individual characters, and count their frequency. So in a sentence, the playground is beautiful today. You just count the number of all the characters individually, and you sort of tabulate them. And this is a nice example that I found. So for example, if your sentence is low, lower, newest, widest, then you sort of take the frequency of each character and attach the number to it. And then slowly you sort of add one character at a time, and you sort of build on your vocabulary. So as you can see, at the end of it, you will have a count pair frequency that look like this. So it's neither like one single character nor this whole word, which is low, lower, and so on. So now we come to the fun part, which is the key gotchas regarding tokenization. So there are these two aspects that I was looking this for. One was, this is for someone who is sort of a prompt user, which is, I think, probably all of us. And if someone is saying no, then I don't know, maybe you're lying. So, yeah, so if you're a prompt user, this thing is good to keep in mind. So for example, you should understand that if the tokenization is bad, then your expected output would also be bad. And we'll see fun examples ahead. Yeah, so next coming to, now, I mean, we'll see this example soon, but next coming to my topic and also this other direction that I want to talk about. So there's this parameter that we calculate called Surprisal. So Surprisal is a language-related, language-theoretic, language sort of comprehension theoretic measure that says that the processing difficulty of a word is inversely proportional to how easy it is to read. So if a word is very difficult to read, you will have some sort of energy utilization to understand it. For example, if I say, for breakfast, I had a laptop. So when you hear the word laptop, there is something that will happen in your brain, because you, like, what happened? You have this activity in your brain. And the idea is that this activity is directly kind of proportional to how unexpected the word was in that context. If I tell you I had an orange, for the breakfast I had an orange, you are like, okay, carry on your life, I'm into apples. But you will not have this spike. So yeah, so you'll not have this spike. Now to use this sort of theory using LLM, what would you need? You would need the next word prediction, because if you have a sentence like, for my breakfast I had, how would I say that orange is more probable and laptop is less probable? You need this next word prediction, right, to measure this. And yeah, so to measure this, you need this prediction. But then to predict this, you actually need to understand how encoding is taking place, how tokenization is taking place. So as you can see, this graph between difficulty and the probability is kind of related inversely. Yeah, so now gotchas while calculating LM metrics, the fun part is here. So now looking into the next word prediction, the match between is the sentence. So what would be the next word? Could be between some team and some another team, the match between, anything, a football club, another football club, and whatnot. So if you sort of use GPT, if you use Transformer API from Hugging Face GPT-2, you will see the tokenization of this sentence is something like this, the match between. And so here you can see this space kind of is included in the word itself. So the match, in the word match, the space is included. In the word between, the space is included. So what does it say? It tells us that the vocabulary of GPT-2 includes not only between, but also between with this inclusion of this space. So if you convert this, you will get this tensor. And now if you look at the next word probability, these are the next word that ChatGPT or GPT-3 in this case would suggest, which looks very legitimate, right? Like the match between the match between them, the match between Chelsea and, I don't know, Sal Madman or someone are Chelsea fans because it pop up so high. Yeah. But if you change it a bit, if you change it just so ever slightly, so if someone who does not know under the hood what is going on, which I did not initially, so that's why that's where this learning is coming from. So if you instead here write the match between and you give the space at the end, now when you sort of predict, it will not put Chelsea there. So so now the encoding looks something like the match between and space Okay, so this space is a different character. It has its own encoding. It has nothing to do with this part of being between. So it's a separate entity in its own, separate encoding in its own. So now if you see, it changes completely. Like this is gibberish. So just with one space, your whole sort of theory of surprisal, right? If someone doesn't know, it's like, oh my God, theory of surprisal, 30 years of understanding surprisal is gone down the drain because they are now predicting the match between ik and so on. So just this small space sort of change the whole dynamic of your next word prediction. So what happens when we get this encoding? So first of all, we have the encoding that, for example, match is represented by 2872, and then you sort of train an embedding vector. So for every sort of token, you have to train a vector, embedding vector, that goes as an input inside a model, and then you see good things happen because every word, I'm saying it loosely, token, every token would have its own representation that will get trained over time. So at the end of it, you would hope that football and Chelsea are closer, Chelsea and chess are also closer, but chess and laptop are further away maybe. Not these days, but yeah. Yeah, what could be the cause of this? Maybe GPT was trained on this form more than the next one, where spaces are not actually the separators, but actually the whole word in itself is coming as a separate entity. So you would have match, you would have a space match, and you would have a match, and so on. Yeah. Key gotchas regarding tokenization. We talked about the first challenge. Now we talk about the second challenge, which is a bit more fun for me. So for an ML engineer, it's important to understand the impact of training data mismatch between tokenization dataset and what is defined as a token. So, so what's happening in the next slides, what will happen is that okay, I'll just go to the next slide, I think, because of the time. Yeah. Yeah, so there were a lot of gotcha moments in the last couple of years in ChatGPT's history, which which was really entertaining to follow. So first of all, there was this word called David Gel, and whenever you try to put this word David Gel, it just doesn't work with ChatGPT. You can just say print David Gel, and it will give gibberish responses, and so on. And then, yeah. So, but why is this happening? It's happening because David JL is actually a Reddit account that used to have a lot of posts on this subreddit called counting, where people are just counting 1, 2, 3, and so on. So because of that gibberish input to probably their tokenization mechanism, David JL is its own entity in this 58,000 word set. Imagine gibberish, total gibberish. But the mistake was that you derived your tokenization from the whole subset, but probably in the training you did not include your Reddit gibberish dataset. So now what happens is that GPT-3, 4 doesn't have any clue about what to do with information because David Jail's embedding never got trained. Because David Jail was a token, a very prominent token in terms of frequency, because that's how tokens are defined. But once you put it for training, David Jail never got trained because there was nothing probably in the training data. So David Jail is just a dot in a random initiation stage. So you initiate your embeddings with a random anything, and then you train over time. And David JL never got the opportunity to get trained. And that's why you will have these really faulty responses for David JL, and all because of a counting subreddit where people are just doing 1, 2, 3, 4. And David JL was a lot involved in this. And the second cool thing is there was this library in GitHub called, which uses this use relative image path a lot instead of relative with its right spelling. So because of that, it had again a lot of occurrences, like thousands of GitHub files had this faulty mention. It again went into the tokenization, and but the model has no idea, no training on this aspect, because in the training model training data set probably they did not involve it at all. So something like this has a huge number of occurrences in tokenization. It has its own token, right? Imagine 58,000 words only, and user relative image path ended up having its own token. And the next is the final cake of the night. So there's this nice blog post about less wrong, and what they did, they actually probed this really in detail, and you should definitely read the whole article. They say that all these words that actually not got represented in the training data set end up having a cluster of their own. So they were able to find all of these, or as many as they could, all of these words that were really bad tokens. So for example, pay, signet message, solid gold magic cup, which was the famous ChatGPT moment. So you can see there were like these gibberish, all these gibberish tokens, completely gibberish. And then when you ask the language model, can you repeat back the string and using one of these tokens to me? Nothing else, just repeat it, right? Very easy for my 3-year-old cousin. Nothing else. But then the responses were really outlandish. They were evasive, like, oh no, I cannot respond. It's against my policy. There were a lot of hallucinations, just replying anything, and even being idiotic and being attacking and whatnot. If you want a field day, this was the time. So yeah. So finally, my key takeaways from this is that weird tokens and unpredictable behavior. So when you train, you should keep in mind about what's your tokenization data set is, what's your training data set is, have a solid distinction between them, and be aware of what you are actually dealing with. Because otherwise, doesn't matter if you are the creator of the model will probably kick you in the back because it's just nonsense. But yeah, of course, it has a lot of implications for interpretability and safety. Understanding this space improves interpretability, and you really need to think and take care of it very well, so as not to have a bad experience for anyone. And finally, your jobs are safe as long as you don't rely on everything, as long as you don't rely on AI for everything, especially your code, check it 100 times. Maybe sometimes it's even faster to do it by yourself. Okay, you can do it. I trust you. You are here. We'll get through this together. Okay. And lastly, 3 resources. So if you have a lot of time, go through all 3 of them. If you have less time, go through 2 of them. And if you have no time at all, take out 2 hours and go through Enric Karpathy's very good detailed video on tokenization. And that was on time.
Thank you very much, Siddharth, for such a fun talk. Anyone have a question?
Thank you. It was really interesting. I am in no means an expert in this field, but I'm wondering, would you have any suggestions tokenizing the Lithuanian language? I think that the reason that it's hard is because we have a lot of cases, and then the endings are different, but the word is the same, the stem is the same.
Yeah. Yeah, I mean, I don't know much about Lithuanian, but yeah, I mean, it's a challenge. It's a challenge. A lot of, for example, in Indian languages, there is a whole discussion around it because there are like 50 or 100 languages. But I think they have mostly concluded, sadly, that I think comes at the end, it comes to how much data you have. I think you can train everything these days. Yeah, so that's the point. But I think for example, with this Indic language, at least I mean I can talk about Hindi and Indic languages because we have a lot of this combinations of vowels and consonants which are not really easy for our English native to understand. So in that case, I think it's quite common to use the very character-based encodings because so that you can cover everything because it's very difficult to really build ground up from it. So for these languages that are Unicode, uh, just character-based probably is better. Yeah. Thank you.
Thank you. At least if speaking about GPT models, I was so surprised that multilingual models have approximately 100,000 tokens, and that's all. So it probably explains why such small languages as Lithuanian, they are not covered well.
Yeah.
Because they, you know, one model have to accommodate more than 100 languages. So we probably, all words are just composed from characters, as you mentioned, or couples of characters. So the dictionary size matters a lot, and this is the weak spot, as I guess, for now.
Yeah, I think I think it's about the data set you train on. Tokenization is still limited, right? Because you have limited number of characters. But yeah, when it comes to the next part of it, I think what you said is on spot. Yeah.
Hi. Is there a way to control the surprisal element? Does it have something to do with the temperature parameter?
I've not looked into temperature parameter, but I can talk to you about different other parameters probably.
Hello.
Maybe after.
I also wanted to know, I haven't heard about Surprisal before. Is it somehow related to perplexity?
So Surprisal is so in our theory there is an idea that there is an idea in our theory of human comprehension that the that lexical predictability plays a big role. So prediction is the driver. So when we are talking right now, you are actually predicting on the fly what I'm saying without even really you cannot stop it. If it, I mean, if it's not your language, it's easy. But if it's a language that you understand, you cannot stop it. It's like you cannot really close your brain. So the idea is that if something that you predicted is right on spot, then you don't have to do much work. So for example, I had in the morning I had for breakfast bread and butter. So that's something when I say I had something in the morning, you already have a concept of what I may have out of these 100,000 possibilities or whatnot. So when this matches with what you want to feel like, it works. When it doesn't, you have this correction in your brain. So I don't know if it's right. It's not. Maybe it's not. Maybe it's in some way related to perplexity. But the way we define it, it's about word given the context, probability, conditional probability. So again, keep on giving this breakfast example. It also makes me hungry. Maybe I should change the example. But yeah, so in this example, for example, in the morning, I went out for a walk. I think this is better. I went out for a, and then you have this walk when you want to calculate the surprisal on walk. Then you will have this conditional probability that given in the morning I went out, what is the probability? So we are more interested in this probability, and then we match it with some brain sort of some brain variable. I don't know how to say it. Yeah. So yeah. With yeah. So yes. To map each token with I mean the word with the token, giving the number. Okay. Yeah. So I mean I talked briefly about it, that there are different ways you can have each word represented differently, or you can do this byte pair encoding. Maybe I can tell you in detail after this talk. Okay.
Yeah, thanks for the talk. Maybe my question is quite basic, but you showed us a tool for visualization. What if you find some mistake in this? How to fix it?
Yeah, that's the whole industry. That's why ChatGPT is paying people to create their data sets and take care of it. I think it's a lot of manual labor at the end of the day, because there is literally, because if there are 60,000 tokens you have created, you might have to do some manual labor as well. Yeah, the idea is that what you build your tokenizers on should be very close to what you're training it for. So if you in your tokenization you talk about chess, and you are training a model that does not include chess at all, then if I ask the model, hey, would you play chess with me? Maybe the model will still make some sense. But if I just say chess question mark, the model will just reply something random, because it was never trained. The embedding of chess was never trained. It's in the tokens, but it's never in the training data set. So you have to have it in the training data set.
Thank you very much.